Now here we get this separated into variable v on the left hand side and variable x on the right hand side. Now this is clearly using the partial fractions through which we are going to split. So using partial fractions for the left hand side of this of dv is dx by x of dv. So using the partial fractions on the left hand side, this reduces to 1 by 3 times of 1 by v plus minus 3 of dv is dx by x. Now integrating on both sides, we get this to be integral of this is integral of this. So once I integrate this, I get this to be minus 1 by 3, and integral 1 by v dv is log v. And integral of 2v minus 3, 1 by this, is log mod 2v minus 3 by coefficient of v, which is 2. And then on the right hand side, integral of dx by x is log mod x plus c. So eliminating the log, we get the final answer in terms of y by x. Next, further simplifying this, we get this to be minus 1 by 3 of log v plus this can be used as log v root of 2v minus 3 is equal this plus c. So this, on further simplification, taking 3 to the right gives us minus log v root 2v minus 3 minus 3 log x is c. So taking all log terms to the left and taking this on the right, I get log mod v root 2v minus 3 plus 3 log mod x is minus c. Then taking the formula log a plus log b is log ab, and log a power m is m log a, and log a plus log b is log ab are the two basic logarithmic formulae which we are going to use here. So log a plus log b into x cube equals minus c. That implies minus c I can take as log c dash. So eliminating log, we get v root 2v minus 3 of x cube equals some c dash is how we get. Then cubing on both sides, we get the required answer. Continued. Now continued from here, we observe that as we take this to be some constant, I take this as c dash and this reduces to some c. And this integration constant gives us squaring on both sides. I get this as x power c v square of 2v minus 3 equals some c square is how we get when we square on each side. But we know that y is vx, that implies v is y by x. Now we want to retain back the original variables x and y. So therefore, we are going to take v as y by x and substitute in this equation. That implies x power 6 v square is y by x whole square, and 2v, which is y by x minus 3, is c square. So this, on simplification, gives x power 6 y square 2y minus 3x. Now as we see here, this is y by x, so y square by x square times of x, which becomes x cube times this equals c square by taking LCM and multiplying x with x square. This on further simplification gives this as a x cube. Therefore, we get the final answer as x cube y square 2y minus 3x equals c square. Or this can be adjusted as some constant k, that is x cube y square 2y minus 3 is equal to some k, because the constant or the arbitrary constant can be replaced for any k in general, and therefore the general solution of the given homogeneous differential equation is x cube y square times 2y minus 3x equal to k, using the homogeneous method, substitution of y equals vx. Next is the limitations of homogeneous differential equations. Now that every method has its own limitations, let's discuss the limitations of homogeneous differential equation. Now clearly we know that this method is used, or the method 2 is used only when the function is homogeneous. What if the function is non-homogeneous? Is where the limitations are more important. Homogeneous differential equation is solved using y equals vx if and only if the differential equation has a homogeneous function. This it fails if the function is not homogeneous. It fails in solving non-homogeneous differential equations, say for example like x minus y plus 1 by 2x plus 3y plus 4, where in case of these kind of problems I cannot take y equals vx. This method will not help in solving the non-homogeneous differential equations as the case, and hence it is limited only to homogeneous functions where I can solve using y equals vx. Let's see the learning outcome of homogeneous differential equation. As we have clearly seen that homogeneous differential equation indirectly uses variable separation method, as seen in the previous case where we separated the variables x and v's. Therefore, here the learning outcome is that method of solving the homogeneous differential equations uses indirectly the variable separable method is how we understand the separation of variables in using homogeneous differential equations are very much connected. Method 1 and method 2 are connected because method 2 can be used only if method 1 is applied indirectly in the method 2. Now there are two cases through which we solve the non-homogeneous differential equation. In the previous case, we have seen homogeneous differential equation which can be solved using the method starting with y equal to vx. What if the differential equation is not homogeneous? Let's see the method 3, which is solving of non-homogeneous differential equations. Solving of non-homogeneous differential equations has two cases where generally a differential equation in the form dy by dx equals ax plus by plus c by a dash x plus b dash y plus c dash is solved. Clearly this is a non-homogeneous differential equation because the right hand side function is non-homogeneous. The degrees are not same. So solving of this non-homogeneous differential equation has two cases of process where the first case is if a by a dash is equal to b by b dash, and the second case is if a by a dash is not equal to b by b dash. So with these two cases arising, initially we check for this equal to this or this not equal to this, and hence we differentiate case 1 and case 2. So each of the coefficients of x, y of the numerator and denominator are checked for this, and if suppose this is equal to this, then that implies we take equal to u, or we take this as equal to v. And if suppose this is not equal to this, then we proceed with some other process where we substitute x is x plus h and y is y plus k, where h and k is the point of intersection of these two lines, where hk is the point of intersection of these two lines is how we find. So taking this and this solved, we get the point of intersection of this and this, which is h comma k. The x coordinate is h and the y coordinate of the point of intersection is k. So let's see in brief both the case 1 and case 2 respectively for a non-homogeneous differential equation. Now let's see the solving of non-homogeneous differential equation initially with case 1. So let's take an example problem which involves case 1 of solving the non-homogeneous differential equation. That is, if I have the question which says solve the differential equation dy by dx equals x minus y plus 3 by 2x minus 2y plus 5, then clearly I see that this is in the form ax plus by plus c by a dash x plus b dash y plus c dash. So the given differential equation taken in the form this clearly gives a equals 1, b equals minus 1 and c equals 3, and a dash equals 2, b dash equals minus 2 and c dash equals 5 when compared with the original non-homogeneous differential equation. Now in case 1 we check for a by a dash, which is nothing but 1 by 2, and b by b dash, which is minus 1 by minus 2, which is 1 by 2. Therefore clearly I see that a by a dash equals b by b dash equals 1 by 2. Therefore this comes under case 1. So under case 1 we know that if suppose this equals this, then immediately I take the first part of ax plus by equal to some u. Therefore by case 1 let x minus y equals some u. Then in this case differentiating on both sides with respect to x, we get 1 minus dy by dx equals du by dx, which on further simplification gives dy by dx equals 1 minus du by dx and x minus y equal to u. So I'm going to substitute this and this in the given differential equation. So let's see what happens when these two are substituted in this differential equation. Therefore, substituting these two equations in the given problem continued, we get dy by dx, which is 1 minus du by dx equals x minus y plus 3, that is u plus 3, by 2x minus 2y, that is 2 times of x minus y, is 2u plus 5 is what we get. And therefore, clearly I see that this is reduced to a variable separation method where I can separate them into two different variables. So let's see how we can do that. This, on further simplification, gives du by dx equals 1 minus u plus 3 by 2u plus 5. And this, on simplification, gives 2u plus 5 minus u minus 3 by 2u plus 5. That implies du by dx is 2u minus u, which is u plus 2 by 2u plus 5. Then separating into variables, 2u plus 5 by u plus 2 of du equals dx is what we get. Is what we get when we simplify this 2u plus 5, which can be written as 2 times u plus 2 plus 1 by this du equals dx. Continued from here, I can split this using 2 plus 1 by u plus 2 of du equals dx. Now integrating on both sides, I get integral 2 du plus integral 1 plus 1 by u plus 2 du equals integral dx. Then integral 2 times du is 2u plus log mod u plus 2 is x plus c. U, which is nothing but x minus y, x plus c. This x, when brought here, comes as 2x minus x, which is minus 2y, plus log mod x minus y plus 2 equals c when substituted with u. Therefore, the equation or the solution of the given homogeneous, non-homogeneous differential equation is given by the solution as answer x minus 2y plus log mod x minus y plus 2 equals c, where c is an arbitrary constant, using the variable separation method of case 1. So this is the case 1 of solving non-homogeneous differential equation. Now let's solve a non-homogeneous differential equation which involves the case 2 of the method. Now in this case of the third method of solving using case 2, let's take an example problem which involves case 2. For example, I wanted to solve the differential equation dy by dx 2x this 2y plus x plus 1. Then This is clearly a non-homogeneous differential equation in the form ax plus by plus c by a dash x plus b dash y plus c dash. Now rearranging them in the form of x and y, this gets reduced to dy by dx equals 2x plus y plus 3, and x term comes out here as x plus 2y plus 1. Now clearly comparing this with a is 2, b is 1, c is 3, a dash is 1, b dash is 2, c dash is 1. Now to check for a by a dash, which is 2 by 1, which is 2, and b by b dash, which is 1 by 2. Therefore, clearly I see that a by a dash is not equal to b by b dash because 2 and 1 by 2 are not equal. So this clearly comes under case 2. Therefore, this involves using of case 2. So in case 2, we just take x equals x plus h and y equals y plus k. So using these two, let's see how the given differential equation reduces to capital X and capital Y in terms of x and y substituted there. Therefore, the given differential equation when substituted with x plus h and y plus k reduces to x plus h of this by x plus h plus 1, where the small x is replaced with capital X plus h and small y is replaced with capital Y plus k, where h and k are constants, is how we understand. So expanding through brackets, this comes as 2x plus y plus 2h plus k plus 3, and this is now clearly the left hand side. When x is x plus h, then dx will be d capital X and dy is d capital Y, because differentiating of a constant is 0, so dx is dx, dy is dy. So dy is replaced with dy by dx, which is equal plus 1 is what we get. Now this differential equation is now compared with the case 2 of the non-homogeneous differential equation and its solution. So here h and k is obtained by equating this and this to 0. H and k are found by this equal to 0 by solving the two equations. This equals 0 and this equals 0 is how we set, and h plus 2k plus 1 equals 0 is how we solve these two in order to get h and k. So in every problem of non-homogeneous differential equation with case 2, we reduce the given equation into this form, and then this and this are solved to get the values of h and k. So let's find h and k using the elimination method. This gives us 2h plus k plus 3 equals 0, and multiplying this with 2h plus 4k plus 2 equals 0. Then k minus 4k is minus 3k plus 3 minus 2 is 1. That implies k is 1 over 3. And when k is 1 over 3, we find the value of h. When substituted gives h plus this, when substituted in this, gives us h equals 2 by 3 plus 1, 5 by 3, which is negative 5 by 3. Is what we get. Therefore, the two values of h and k are h is minus 5 by 3 and k is 1 by 3 is what we get. Therefore, my x is x plus h and y is y plus k. Using this, I get h is minus 5 by 3 and k is 1 by 3, which I substitute in this after solving the entire differential equation. So with these values of h and k, this differential equation reduces directly to this 2x plus y by x plus 2y. With these two being equal to 0, they get eliminated. Continued. Therefore, by substituting h and k in the transformed equation, we get dy by dx as 2x plus y is x plus 2y is what we get. Now this is clearly, as seen, is homogeneous differential equation in x and y of degree 0. So clearly this is a homogeneous differential equation in x and y of degree 0. Therefore, by using the second method of solving the homogeneous differential equation, we take y equals vx and then differentiate both sides with respect to x. Differentiating both sides with respect to x, we get dy by dx equals v plus x dv by dx using the product rule of the differentiation. So substituting in equation 1, we get v plus x dv by dx equals 2x plus y, which is vx, and x plus 2 times of y, which is v of x, is how we get. Then simplified. Then this, on taking x common and simplified, we get 2 plus v by 1 plus 2v, which needs to be eliminated using the separation method.